Welcome, everybody. My name is Cliff Grossner, and I'm the Chief Innovation Officer for the Open Compute Project. And today we have a discussion around hybrid AI network and their deployments. One of the reasons that we thought it was appropriate to have this webinar on an OCP platform is that we all recognize that AI is the top use case driving the current build out of computational infrastructure. But while everyone's been focused on the builds of the very large data centers and tracking that, we also know that as we move forward, AI will be deployed in many, many locations, from the cloud to the on-prem data centers, and perhaps even on personal devices. And so it makes a lot of sense for us to understand how networking is going to play a key role in that deployment, and really the way that we're going to need to engineer the networks to make the whole system work as a success. I would like to introduce our other two panel members for today. We have Sami Boulaben from the Laurel Group, and we have Praful Lachalandi with us. And both of them have a number of years of experience in sizing markets and with dealing with network deployments. And we look forward to hear their insights today. We're going to kick it off with Sami, giving us a bit of a view of what's going on in the market and the interaction between cloud and on-premise deployments. Then we'll have Praful chat about how AI training is going to be important and how Ethernet's going to play a key role in delivering performance. We're going to also take a look at the emerging network architectures that are going to apply for inference, as those will certainly be deployed widespread in the long run. We'll allow Praful a few minutes to talk about the sponsored products from Juniper, and then we'll have Sumi wrap it up with a joint little conclusion. Now, along the way, we have several poll questions for the audience, so stay tuned. And also, we will have a live Q&A at the end. So as we move along, please enter your questions in the question box. So with that, Sumi, over to you.
Thank you very much, Cliff, for the introduction and the background. So I would like to start on this chart to remind the audience of the architecture of AI networks. So here on this chart at the very top, we see the traditional network used to connect general purpose servers. This is known as the front-end network, which relies entirely on Ethernet. The market for data center switches deployed in the front-end network is currently valued at about 20 billion, with an estimated CAGR of 7% over the next 5 years. Now below, in green, what you see there is the network used specifically to connect GPU to GPU or accelerator to accelerators in general. This is what we call the AI back-end network. This is a new network that emerged to support the large AI clusters, which are often consisting of tens of thousands and even hundreds of thousands of GPUs required to run large AI workloads. This network is currently a mix of InfiniBand and Ethernet. And today, the market for data center switches deployed in the back-end network is valued approximately at 3 billion, and it's expected to grow by more than 50% CAGR over the next 5 years. Now, on this chart, I would like to talk about the various AI models, who is building them, and what type of infrastructure is being used to run those AI workloads. So here we look at the market by customer segment. At the very top, we have hyperscalers, governments, select startups, and research labs. And in general, these are the major customer segments that do have the financial and human resources to build the needed large training models that we call foundation training models. They may also be building large inferencing models, and they will be running most of these AI workloads in their own data center infrastructure. Next, we have tier 2, 3 cloud service providers and large enterprises. And in general, these customers will be mainly fine-tuning pre-trained language models or building small inferencing applications. And these models are expected to be moderate in size and may not require more than hundreds or maybe a few thousands of GPUs at the most. In terms of infrastructure, these customers will be adopting a hybrid approach by using a combination of on-prem and off-prem infrastructure depending on the data gravity, data privacy, and latency requirements of the various AI workloads. Now, on this chart, I have a forecast of the AI backend network by customer segment. And the key takeaway here is that we expect the contribution from enterprises to the AI backend network to grow from less than 5% in 2023 to more than 15% in 2028. The contribution from rest of the cloud also is expected to grow significantly over the next 5 years. And we have actually raised our forecast for the enterprise portion of the market with our most recent report because we've been witnessing an accelerated pace of enterprise adoption of AI. We do believe the next wave of AI adoption will be driven by enterprises, and we're already seeing certain verticals such as finance, healthcare, government, and automotive investing heavily in building their own AI infrastructure and becoming very quickly multi-billion-dollar opportunity as they realize that AI will basically help them enhance productivity, boost revenues, and also gain a competitive edge. Now, one of the hot topics in the industry is which fabric is the most suitable for these AI workloads. Is it going to be Ethernet? Is it going to be InfiniBand? On this slide, I have a list of considerations that we discuss in more details in our AI network report. And we look at the influence of nature of workload and cluster size. We also look at the end user distinct choices and architecture. Different customers will make different, as you know, will make distinct choices based on various considerations, especially the hyperscalers. We all know that each one of them has a different strategy. But in general, what we're observing is that enterprises and tier 2, 3 cloud service providers do have a high affinity for Ethernet. We also look at NVIDIA GPUs versus non-NVIDIA GPUs. The latter will most likely go with Ethernet. And last but not the least, we look at the influence of the ecosystem and roadmap development. As you know, AI workloads do have requirements that are different from traditional workloads, and therefore the industry needed to add enhancement on Ethernet to tune it for AI workloads. And more recently, we have been observing new enhancements at many levels, including network chips, server NICs, switch systems, optics, software, and so on and so forth. Now, here we look at our forecast for InfiniBand versus Ethernet in the backend network. We currently forecast Ethernet to surpass InfiniBand by 2028. And this optimism in favor of Ethernet stems from improvement on both the supply side as well as the demand side. So as I've already mentioned, on the supply side, we're seeing more Ethernet switch products tuned for AI workloads being introduced to the market with competitive performance compared to InfiniBand. And on the demand side, few things are favoring Ethernet. So first, we're seeing the proliferation of non-NVIDIA accelerators. Second, we're also seeing increased adoption of AI from enterprises and tier 2, 3 cloud service providers. And as I mentioned earlier, these customer segments tend to favor Ethernet. Third, even for the large scale clusters, we are seeing increased appetite for Ethernet. We're seeing multiple large cloud service providers shifting from InfiniBand to Ethernet. And the most recent announcement was for a cluster with 100,000 GPU running with Ethernet. Now, on this chart, I also wanted to touch on the speed adoption aspect in AI backend network. So unlike the front-end networks, which are compute-bound, the bottleneck in AI clusters is actually the network. Given that the GPUs are very expensive, you really need to make sure that the network is operating at nearly 100%. On top of that, the refresh cycles in AI backend networks are very short. Usually they are 2 years or less, compared to 5 years in the front-end network. And that's exactly why, if you look at the speed transitions in AI backend networks, they are very fast. They are approximately twice as fast as the speed adoption in the front-end network. And as you can see here, we expect that by 2025, the majority of switch ports in AI backend network will be 800 gig, and by 2028, the majority will be 1600 gig and even higher. With that, I will pass it over to Cliff to run a poll question.
Well, thank you, Sameh. And I guess we wanted to sample the audience on the poll question around where does your organization do AI training? And Kevin, I'm trying to understand where our poll question is. Okay, I think we'll come back to the poll question later. Sorry about that. We'll keep going then. So, Praful, let's go over to you and have you talk a little about Ethernet for AI training.
Thank you, Cliff and Sameh, and good morning, everyone. So let's take a look at why networking is important in the first place in an AI cluster. So we know that GPUs are the currency for the AI revolution, but we also know that GPUs are super expensive. Even building a small cluster can cost you a capex investment of $5 to $10 million. And now if you're talking about thousands of GPUs, they're easily running a capex investment of hundreds of millions of dollars. Now, while networking as a percentage of that total investment might be a small percentage, it plays still a crucial role in maximizing the performance of GPUs. Because if there is any bottleneck or congestion in the network, it leaves your GPU sitting idle, and that's not something you want from an expensive infrastructure. Now, let's try to appreciate why networking is important at an even more granular level. So what happens is that AI training in specific is a distributed computing problem. That means that it's not just one GPU that is being used to train your model. You typically have tens to hundreds or sometimes even thousands of GPUs that are working in conjunction in order to train your model. And in order to be able to do that, what we are seeing over here is an example of model parallelism abstracted at a 10,000 foot level, where data is chopped into chunks and distributed over to the GPUs. Then GPUs all do their computations, which is basically they are updating the weights and biases of their neural network. But when the GPUs finish their computation, they have to merge their computations. And when that merge of computations happens, that's when burst of traffic hits the network all at the same time. And that's why the network is important, because if there's any congestion in the network when that burst of traffic hits the network, it slows down the entire computation, because the whole computation merge cycle keeps repeating itself over and over again. And until all the merges are finished, the next computation cannot start. So say that more explicitly, if there are 100 GPUs in your cluster and GPU 30 is not talking to GPU 40 fast enough, or there's some congestion or drops in the network, all GPUs are sitting idle. And that introduces the concept of tail latency, which is the entire effort in improving the Ethernet performance is around eliminating that tail latency and eliminating that bottleneck in the infrastructure. Now, Sameh has alluded to this, that there is foundational model training and there's fine tuning. But whatever, whether you're doing foundational model training, which is training a model from scratch, or starting with a pre-trained model and adapting it for a task-specific data set, which is fine tuning, the network infrastructure for AI training kind of remains the same. The scale varies, but the kind of the design kind of remains the same. So you have a front-end network where client request comes in. This is where your shared storage nodes exist. Your orchestration, whether it's done by Kubernetes or Slurm, is happening from over the front-end network. But most interestingly, you have these back-end networks. Back-end network, for example, the back-end GPU network is for GPU to GPU connectivity. Like I said, all GPUs need to merge their computation, and that's happening over the GPU network. And then you have the back-end dedicated storage network, which is for GPU to storage connectivity. Now, job completion time is the critical metric in AI training, which is really measured as how much time does it take to train my job with a specific data set and a target accuracy in mind. Now, in that backend, Samay has alluded that there are two technologies at play. There is InfiniBand, and then there is Ethernet, which is emerging as the next class of technology for that GPU backend in Fabric. And InfiniBand is something that was the gold standard for high performance computing that happened on GPUs. And when the AI wave picked up, obviously AI had because of the massive parallel processing capabilities of GPUs, AI training and AI inference was naturally migrated over to running on GPUs as well. And somewhat InfiniBand kind of got pulled through in that use case as well. But many enterprises and cloud providers realize that InfiniBand is a vendor locked-in proprietary solution today. The tooling and the skill set that you have available for Ethernet doesn't really exist for InfiniBand to the same extent to manage and operate InfiniBand networks. All of this leads to a higher total cost of ownership of InfiniBand. And plus, as the ecosystem of GPUs advances from just NVIDIA today to AMD to Intel and other accelerators out there like Cerebras and Grok and Sambanova, InfiniBand is locked in sort of to your NVIDIA technology, whereas Ethernet is open to work across all of these. So while these advantages of Ethernet are visible and apparent, InfiniBand has proven itself for AI workloads, and was incumbent on vendors on the Ethernet side to also prove that Ethernet is up to the challenge. And here at Juniper, at least, what we did was we built up an AI cluster. So this is an AI cluster which has NVIDIA GPUs, it has AMD GPUs, it has Weka high-performance storage, it has alternatively a vast high-performance storage. And we built up this entire cluster and specifically on the NVIDIA side based on the NVIDIA SuperPod reference design, which is the design that NVIDIA recommends all the way up to orchestration with Slurm and everything. And the only thing that we changed was in the reference design was we replaced InfiniBand as the networking technology in the backend with Ethernet as the networking technology in the backend, but everything else kind of remained the same. We use the same rail optimized design that NVIDIA proposes for as part of their reference architecture. And we put it to the test in this lab. We put Ethernet to the test in this lab. What we did was we ran several ML perf models from ML Commons. Now, if you're not familiar with ML Commons, that's an industry body that produces benchmarks. They produce standardized data sets and standardized models so that when vendors are comparing performance, and if they pick a benchmark from ML Commons, they can do apples to apples comparisons. So in this particular example, we ran, for example, PERT large, which is a large language model, and we achieve a job completion time, which I said was a critical metric in AI training, at 2.6 minutes. 2.6 minutes versus InfiniBand reported numbers that range from 2.5 to 3.3 minutes, right? And these are all published on ML Commons. So here we basically proved that Ethernet is really up to the challenge. It's not just BERT large that we have run. We run Llama to Nemo, we run GPT-3, we have done Llama 3 as well. So we have done a lot of different models, and we get very good results over Ethernet. So the next question might be, how does Ethernet deliver, right? Yes, we saw the results, but how is it exactly deliver? And the first thing, no shame in saying, throw bandwidth at the problem, and to a certain extent, the situation alleviates, right? And Ethernet in recent years has been on a tear, really, right? So for example, today we have 400 gig solutions have been ready for quite a while, and they've been used for interconnecting to the NVIDIA Hopper class or the H100 or H200 class of GPUs that operate at 400 gig. But Ethernet is ready even for the Blackwell generation. So we know that Blackwell GPUs, as when they come out, they're going to be able to drive 800 gig of network traffic, and Ethernet is ready with that technology even today. So for example, Ethernet switches based on Broadcom Tomahawk 5 have been shipping since Q1 of 2024. And we are already on a path to 1.6 T at this moment, and have that Ethernet will have that ready in early 2026 or maybe even late 2025. Now, if you compare to InfiniBand is always a little generation behind in terms of speeds and feeds. The highest speed available is 64 ports of 400 gig. They've announced a 800 gig solution, but it's only going to ship in volume in 2025. Now, 800 gig is not just for the Blackwell series, though. Even Ali, what we have seen, as Ali Samay showed, we started seeing a migration towards 800 gig, even to connect to the Hopper or the H100, H200 class of GPUs. This is because an 800 gig port can split into two 400 gig ports, and you can have 400 gig connectivity to the H100, whereas in the fabric, you can get a performance boost with 800 gig. And now you're building the same size cluster with less number of switches, half the number of leaf switches, less number of optics, so total lower cost of ownership and lower power consumption as well. Now, the second thing is it's not just about hardware. It's also about a lot of software capabilities to mitigate and avoid and congestion in the network. And the reason for that is classical Ethernet suffers from an issue where you can still see congestion in the network even if you have enough bandwidth in the network. So if you see on the picture on the top right, you have two 400 gig flows that are coming in from GPUs, and they may be mapped to the same 400 gig uplink to the spine, even though you have multiple spine links available. And this is because Ethernet uses, static ECMP, or a classical Ethernet uses static ECMP using a 5-tuple hashing to decide which uplink path to take. And you might have multiple flows come in, 400 gig flows come in that are mapped to the same path. And you can have a similar problem on the downlink on the top left. So you have multiple leaves, leaf 2 and leaf 3, that made independent decisions to send traffic to the same spine. And then now you have collisions on the way down from the spine 1 to leaf 1. And this problem is further exacerbated in AI networks because you have fewer, larger flows. In a classical TCP network, you have thousands and thousands of flows, so your entropy kind of manages itself. But in AI clusters, you may see a polarization of traffic in your fabric. So the solution for that is, what we call congestion avoidance, is really different load balancing techniques that can be used in Ethernet to evenly utilize the leaf spine capacity in your fabric. So let's see what those are. So first we will start with something called dynamic load balancing. Now, dynamic load balancing is a load balancing techniques where it accounts for the quality of a link instantaneously to make a decision on which path it should take. So for example, I just said static ECMP or static hashing in classical Ethernet decides that it very, very statically decides which path to take, and you may have collisions on that path. But now what if you could monitor the quality of the link based on bandwidth, queue depth, instantaneously, so that when the next packet or the next flow comes in, you can divert that packet on the best link. So in this example, G2 is sending traffic to G6. I have 3 available paths on leaf 1. The quality of 2 paths is not that great, so I'm going to send that traffic over down to the best path. And what we have seen with this is that leads to like a very, very even utilization of traffic across your Ethernet infrastructure. So in fact, again, we put that to the test, and we ran another model from MLPerf. This is called DLRM, and we're measuring the job completion time. So lower is better. And what you'll see is that as you start adding more background traffic in the infrastructure or over your fabric, static hashing over here on the left-hand side of the graphs deteriorates pretty badly. Whereas DLB, whether you're using per packet DLB or flowlet-based DLB, the performance does not degrade, even though you're adding more and more congestion in the network. So this is an important feature for Ethernet networks. As an extension to that, there is also something called global load balancing. The idea behind global load balancing is that I make a quality decision not just on my local path, but on my remote path as well. So again, G2 is sending traffic to G6, but imagine Google Maps, right? So now if I'm driving, I can see the congestion in the road in front of me, but Google Map will tell me that there is congestion 3 roads down as well, so you should take an alternate path, which is exactly what GLB is doing over here as well. So now G2 sending traffic to G6, it observes that my local quality through S1 is bad, but my remote quality is also bad between S2 and L3. And with that awareness, I'm going to send all my traffic, or I should send the next burst of traffic or packet through S3 until that congestion alleviates. And this monitoring is happening at pretty much real time. It's happening in microsecond granularity, so that switch leaf 1 can make its decisions more intelligently. And if that doesn't work, there is a measure of last resort called congestion control. Now, some of these techniques have been existing in Ethernet for a long time. It's just being adapted for a new use case. But the idea behind congestion control is that if congestion avoidance did not work, then you don't want any drops in the traffic. You have to tell your source to slow down. So for example, with explicit congestion notification, if a switch sees a traffic drop, or it starts seeing, not even a traffic drop, if it sees buffers filling up, it knows that there's going to be congestion happening, it's going to send a notification to the source to slow down. And priority-based flow control is really a link-to-link mechanism. So if a receiving switch starts having buffers fill up, it's going to tell the sending switch to slow down, or actually it's a little pause until the buffers alleviate and it can start sending traffic again. So again, these are mechanisms to slow down the source one way or the other. And with that, I'll turn it over to Cliff.
Well, thank you, Praful. And now we actually have our first poll question for the audience. And so we're looking to get some insight on where your organization is going to do or is doing AI training. Do you see that happening more in the cloud for your organization, on premises, or do you not see that happening for your organization? So take a minute, let us and fill that in as best you can. While people are filling that in, I would like to remind everyone that we will have 10 to 15 minutes of time for a question and answer at the end. We've got a couple of good questions that have already come in, but please go ahead as Praful is talking. If you have any questions, let us know. We're going to do our best to answer as many as we can at the end. Okay, well, let's see how many answers we have. So we got quite a number of people that have responded, and wow, it looks pretty balanced. Quite amazing, actually, for the 70 or so people that responded. A little bit more in the cloud, quite a fair, almost equal amount on premises. And there's quite a number of people that say they don't know. So I'm going to invite both Praful and Sameh to comment. How does that match with what you expected?
Yeah, go ahead, Sameh.
This is definitely a very nice results to support that the decision of where to run those AI training will be a hybrid approach, but definitely I expect it to be more in the cloud than on-premise. So this is definitely a very nice surprise in a positive way that some of the people who really answered these questions are pulling the triggers and making those investments on premise. And I believe that may have to do with data gravity and data privacy and maybe latency issues also. So, but this is definitely good to know.
Yeah, on my side, I know cloud repatriation is happening, especially on the AI side. But I'm actually impressed by the extent of it. I would expect that still a lot more customers would be doing it on the cloud. But I'm happy to see more going on-prem.
Yeah, I'm also surprised by this, and maybe what people are factoring in is, yes, they may have started some experimentation in a small way in the cloud, but when they look at the volume, that's where on-premise starts to become more equal with the cloud. Perhaps that's one way to look at that.
Yep.
A good result, and definitely something to be thinking about as we all set strategy moving forward. So with that, I think Praful is going to share a little bit about some of the new network architectures for inference. So Praful, over to you.
Yeah, thank you, Cliff. So we talked a lot about training, but there is also inference, and inference is really where the rubber hits the road and an enterprise derives value from all their investments in training. But the infrastructure can look very different depending on what your use case is. So for example, starting with the left, you could just have a single node inferencing. In this particular case, a single GPU or maybe the GPUs within a node are sufficient to handle your inferencing client requests. And this, in the case of some cases, might even be on a CPU. It doesn't even need to be a GPU cluster. When you need high performance, when you need real-time interactivity, GPUs definitely help with its parallel processing capabilities, but it could be either CPU or GPU. And all you need is a classical front-end network from where your client requests are coming in. Obviously, latency matters in this because you want to have quick time to first token. And so that's the way the front-end network looks. Now, again, you have the one in the middle is a little bit more involved because in certain cases with large language models, for example, Llama 2 or Llama 3 or GPT-4, if you're using those for inferencing as a baseline, that may not fit into the memory of a single GPU. And so you may need multiple nodes of servers in order to even do a single client inferencing request. So in that case, you have the front-end network, but the same training network that we are using for backend GPU training, you might still need a backend GPU infrastructure for even for inferencing, and it might be shared with the training cluster, or could be completely dedicated. And then finally, we have a new emerging class of inferencing, which is called retrieval augmented generation. I'm going to touch upon this in the next few slides. So I'm going to skip it from this slide, the discussion on this slide. But I want to talk about two key metrics in inferencing. We talked about training. The key metric is job completion time. In inferencing, there are two key metrics. There's throughput, which is how many client requests can you handle in a given second, which is like the efficiency of your cluster. And the second is time to first token. Time to first token is a measure of the reactiveness of your AI inference. So for example, if you're in front of ChatGPT asking a question, is the first word responded in 1 second, or does it take 10 seconds even to get the first response back, right? And in terms where real-time interactivity is important, time to first token is a very key metric. And sometimes balancing these, it's not, sometimes you improve the throughput, sometimes for time to first token get impacted, and vice versa. So balancing it for your application becomes a very, very critical thing. But as promised, let's talk about retrieval augmented generation, or RAG. And RAG really exists so that the output of your LLM, which is being used for inferencing, can be enhanced with more an external knowledge base so that the LLM can respond more authoritatively. Let's take an example of a customer-facing chatbot in this case, right? So if you have a customer-facing chatbot and you want questions being asked are, is this bug fixed in this release? How many new features are available on my version, or whatever the case might be? You want that chatbot to be responding with real-time information, right? So if the bug is fixed, I mean, if maybe the bug got fixed yesterday, but if your model was trained last week or it was trained 1 month ago, then your model is not responding with the most real-time current data. But that's not what you want from your chatbot. Or in certain cases, enterprises might just not have the data scientists and the skill sets and the toolkit to even fine-tune a model. So if you're taking a LLM from let's say you're taking a Llama 2 LLM, or you're taking a GPT-3 LLM as your baseline, you may not have the skill set in your team yet to fine-tune your model with your proprietary data. So the risk of not using RAG is, first, you might not have real-time responses, and second, the issue is that it may not be trained on your enterprise data, so it tends to hallucinate or just give generic responses. So that's where RAG comes to the rescue by adding an external data source. So this is the pipeline of RAG, really simplified, I should say. But let's start with this box on the top right where it says knowledge source. And really the idea behind RAG is that you're going to supplement the LLM's output with external data. And this external data could be your database, it could be a text file, it could be various formats. But what you first need to do is take an embedding LLM to mathematically represent your data source. So basically you need to store those as vectors. Vectors are basically mathematical representations of your external data, and those vectors are stored in a vector database, which is referred to as a knowledge source over here. Now, when the prompt comes in, which could be like, what is the EOL or end of life policy for, let's say, a product in Juniper called QFX 5100, this prompt comes in. But before sending it to an LLM, that query is first vectorized itself, and then you make a search in the vector database for the most mathematical proximity. Now, those responses that come back from the external database now are combined with the original prompt. So if you see in step number 4, the original prompt plus the enhanced context that you arrive, all of this is mathematically distributed to the LLM, or distributed in a mathematical format as vectors to the LLM. And now the LLM generates a response, which is like hopefully a better response that is not generic and it's not hallucinating for you. Now, since this is a networking presentation, like kind of tying it back to networking, that access to the vector database requires high-performance networking. It's a high-performance storage system. It's a vector database that is stored on some shared storage cluster. Again, very high-performance storage. And you need high-performance networking to access that vector database, because a failure to do so will either increase their time to first token, or the LLM might just respond with generic outputs, which you really don't want for your enterprise application. With that, I'll turn it over to Cliff for another poll.
Okay, so hopefully everyone's awake and on their toes. And in this case, we'd like to hear from the audience once again about do you have an idea where your organization is and plans to be on using Ethernet in the AI cluster for backend networks? Are you already using Ethernet in the backend? Maybe you're planning to do that as you deploy your AI clusters in the organization, or there's really no plan to use Ethernet. You're using something else like InfiniBand. While everyone's answering the question, I would also, again, want to encourage people to put any questions you have in the question box, as there are a number of good questions, and would love to. We'll continue the dialogue in just a few minutes on the live Q&A. Okay, well, it looks like we've got quite a number of inputs coming in from the attendees once again. So let's take a look at what the results look like. Okay, well, Sameh, I must say it definitely seems to reflect your assumptions and forecast that, most of people, well, a good chunk, large sizable sums already using Ethernet, and a good number will use Ethernet when they do their cluster deployment. So interesting to see that on this call. Sameh and Praful, please go ahead and add your thoughts on that.
Yeah, I think Sameh will have to update our charts. I think the crossover between Ethernet and InfiniBand is going to happen sooner.
That's as you mentioned, Cliff, that supports definitely an increased optimism for Ethernet, and definitely that crossover point, Praful, to answer your feedback, which is, by the way, great feedback. That's definitely much more optimistic than, let's say, our view a year ago, and we will keep definitely monitoring the situation. There is an increased appetite for Ethernet, again, driven by an improvement on the supply side, but also, as I mentioned, on the demand side, there are some factors that will be favoring even Ethernet further. One of the factors I mentioned earlier, and I will touch on again later, is the proliferation of non-NVIDIA GPUs that we're seeing being deployed. And so more and more we're seeing Ethernet being a very good candidate to run that AI network fabric. And to your point, Praful, yeah, maybe my crossover point is a little bit conservative, but we'll keep monitoring the situation, as I mentioned. The good thing is that I would love to see them also the nature of attendees or the nature of the entities that participated in this poll question, because definitely while we believe that small cloud service providers and enterprises will definitely favor Ethernet, we're also watching for signals from the super large AI cluster builders to embrace Ethernet, and we're seeing more and more move towards Ethernet, at least in the recent months. Definitely we're seeing a lot of headlines mentioning Ethernet being the fabric of choice and displacing InfiniBand. So.
Yeah. I mean, in talking to a lot of customers, obviously, here at Juniper, I see a very different perception from 1 year ago versus now. Like 1 year ago, breaking away from the NVIDIA reference architecture was very scary for customers, because they said, it was like, if I do this, if I break away from InfiniBand, will anything work? I don't know. It's too new for me to know, right? And now, because all these hyperscalers are, publishing results saying, hey, we get good results with Ethernet at scale, thousands and thousands of GPUs. We are also seeing that we don't have those initial discussions about InfiniBand versus Ethernet. It's like, okay, we picked Ethernet, now let's tell us how do we go deploy Ethernet. So we are seeing a change in how we are engaging with our customers as well. Cool.
Awesome. Well, okay, then in that case, Praful, I think at this point we have it teed up for you to talk a little bit about Juniper products.
Yeah, by the way, I'm seeing some very good questions, so we'll come to the Q&A in a few minutes. But just starting with, like I said, the first thing you do is throw bandwidth at the problem. And here's Juniper portfolio. And I will not go over each of them individually, but like as you'll see, we have a good breadth of portfolio across 400 gig and 800 gig across fixed modular form factors, whether it's shallow buffer or deep buffers. We have it for all your front end, back end GPU or back end storage use cases. In fact, Juniper was the first vendor in the industry to actually ship that QFX 5240, which is a 64 port 800 gig switch based on Broadcom Tomahawk 5. So we're the first in the market with 800 gig solution. And Samay talked about, the largest cloud provider in the world had 100,000 GPUs. It's public information. They are actually using Juniper technology for their 100,000 GPU cluster. But it's not just all about just switching. We also lead with operations, and Apstra is our multi-vendor automation platform. So Apstra is a company that we acquired 3-4 years ago, but the platform has been around for about 10 years, which is complete lifecycle management for data center networks. And now we have also enhanced the capabilities to manage AI clusters as well. What's unique about Apstra is multi-vendor. It can manage Juniper, Cisco, Arista, Dell, Sonic. So it's very unique in that way in the industry. And if listeners over here are aware of what Marvis is or familiar with Juniper technology around Mist and Marvis, Mist was a company that Juniper acquired again another maybe 4 years ago. But we inherited this Marvis AI ops technology that customers are absolutely loving in the campus and branch space because it can do predictive anomaly detection and predictive remediation over wireless networks. But now Apstra is now tied in with Marvis, so the same value that you get with AI ops and predictive analytics in campus is now being brought to the data center with this integration between Apstra and Marvis. Now, but I do want to kind of point, so Apstra is a complete lifecycle platform, but I do want to talk about just one or two capabilities that are unique in Apstra that are targeted towards AI clusters. So when you are when you're a network operator and you need to alleviate, let's say, a congestion issue, somebody has told you that my application is not performing well, my AI training job is taking too long or is just aborted. You don't want to have just an isolated view of congestion in the network. You need to have an end-to-end view where that view extends all the way to the host and where congestion happening on the NIC as well. So Apstra has agents sitting on the host where you can collect all of this telemetry information and congestion view. But not only that, we kind of went step further, and we are actually monitoring the out of sequence packets for example, on the NIC. This is just one example. And out of sequence packets, when you receive them on a NIC, and if it's not a smart NIC, is not a good thing. So it requires network tuning in order to alleviate congestion issues or out of sequence packets on the NIC. And we have basically built an application which actually does exactly that. So looks for out of sequence packets and adjusts DLP timeouts on the network in order to mitigate that situation. Now, the other thing that we hear from customers is that while Ethernet, yes, we're going to adopt Ethernet because it is lower cost, it is standards-based, all of those good things that we've talked about. But tuning DCQCN policies on Ethernet to maximize performance is still a manually laborious job. I have to look at congestion metrics from across my infrastructure, my network fabric, and then I'm looking at all those congestion metrics. Now I have to intelligently determine, looking at those metrics, how do I fine-tune my network? And you might fine-tune it once, it might not work, you have to do it again. And it's an iterative process that can take weeks. And no kidding, it can take weeks to do. And in some cases, the network operator might just say, I'll just leave it running as it is because this is just too complex. But that's exactly why we built this auto-tune DCQCN app that runs on top of Apstra, collects all of these metrics, congestion, makes sense of it, and then dynamically optimizes those DCQCN parameters in real time. So reducing the network tuning time from weeks down to minutes. And lastly, I'll just say that we talked about the lab. That lab is not just an internal Juniper resource. It's available to our customers and partners. So you can come and see how we are running MLPerf over Ethernet. You can try it out on AMD gear. You can try it out on NVIDIA gear, Weka and VAST high performance storage. So we built this whole ecosystem out here. But you can also run your custom model. It's not just our models. You can bring your own models and run it on an end-to-end AI ecosystem. And you can also experience Apstra at its best, how it operates and fine-tunes AI clusters. So, reach out to us and we're happy to show you what we have built over here and how it can be usable for your AI cluster. And with that, I'll turn it over to Samay to take us to the finish line.
Thank you, Praful. So I would like to conclude this presentation with a few thoughts here. So clearly, we are at the very beginning of a multi-year AI journey. AI journey has been spearheaded by the hyperscalers, but we're definitely seeing enterprises and small cloud service providers quickly catching up as they realize that under investing in AI poses a greater risk than over investing. And in fact, I have two popular quotes here from Meta and Google. So on Meta's latest earnings call, Mark said that at this point, I would rather risk building capacity before it's needed rather than too late. And Google CEO said, in tech, when you are going through transitions like this, the risk of under-investing in AI is dramatically higher than over-investing. We do believe the next wave of AI will be driven by enterprises, and we expect enterprises to follow a hybrid approach in their AI deployments. And we anticipate Ethernet to be the preferred fabric for enterprise AI deployments, but also even for the broader market, as we discussed earlier, we're seeing more and more or increased appetite for Ethernet in the recent months. So with that, I will pause here and I will hand it over to Cliff to take some questions.
Thank you very much, Sameh and Praful, for the very insightful discussions and presentation. I did want to talk to one question that came in around the potential bias for the poll question. And I will say that certainly in this small sample, there's always going to be bias. However, the assumption that was cited here around most people attending the webinar are owning and managing hybrid cloud infrastructure, it's actually not true. I have a list of, I'm able to see the people that are attending, and there's a very broad mix of vendors and a few hyperscale cloud providers. So yes, I'm sure there's bias, but not quite in the way the audience might imagine. I think the other important question that's coming in might be for you, Sameh, around UEC and its impact in the market. Now, I know from our affiliation with UEC, they're still working on they're still in early days of releasing their spec, and it's going to be a while before it impacts things. But I'm wondering if you have a perspective, what you've heard about it, and if that's in any way adjusted your perception of Ethernet versus InfiniBand.
Very, very good question. And I'm really glad that someone asked this question related to USC. And I have to say, a year ago, a year ago, I think everyone thought that USC is going to be a necessity for Ethernet to really make a dent in the AI fabric. And I continue to believe that USC will be very, very important. And when we see those specifications being finalized and being turned into or reflected in real products, that definitely will also help Ethernet gain even further traction in the AI backend network. But what we were surprised with in a positive way is that even before we get to that USC specification finalization in the process, we're seeing already a lot of the Ethernet products tuned for AI being brought to market, and a lot of the vendors, to Praful's point, it was really a responsibility from the Ethernet vendors to come up with improvement either on the network chip side or software, the NOS, or even to Praful's point, having some sort of a network layer that fill the gaps between the NIC and the switches. All of those improvements actually were important and were good enough for the market to start embracing Ethernet, right? So the short answer to your question is that we do believe USC bringing specifications to the market will definitely help Ethernet, but what is very interesting and important to note is that even before we get there, there is a lot of work that's being done on the Ethernet side. And obviously, when you look at the Ethernet network chips in the market, you have various, choices. Some of the choices, like if you were to go, let's say, with a deep buffer type of chip, or what we call scheduled fabric, you may also, you actually don't have that huge dependence on the NIC side. So it's almost like NIC agnostic. But even if you don't go with scheduled fabric, you also have other options on the NIC side to really help with the performance. So definitely USC is key. I would have loved for USC spec to get finalized faster, but even with that, that's not really preventing Ethernet from gaining traction in the market.
And I'll just add to that one. So UEC is not going to be an on-off switch that, one day
Yes.
you have a UEC capable Ethernet versus one day you don't. So I think measuring that ramp is going to be really hard. And the reason I say that is that if you look at the UEC 1.0 draft, some of the capabilities that UEC is standardizing are already available. So for example, the whole thing about NIC doing tagging of packets so that the switch can packet spray, that solution works today. I mean, we have tested it with Bluefield 3, we have tested it with ConnectX 7. So part of what UEC is standardizing already exists in Ethernet today. Part of it will be available, so through some software enhancements on, let's say, Broadcom Tomahawk 5 or 800 gig products, and some of them will come in Tomahawk 6, and some of them will come in some other variants of chipsets. So it's going to be a slow rollout, and as Samay alluded, Ethernet has already adopted some of those capabilities.
Okay, thanks. We do have another question that I think is a little bit more in Praful's camp. Is there any measurements that you've done around the overhead of dynamic or global load balancing compared to static load balancing?
I think the question is probably, to be more explicit, is probably, is there a latency impact? And there's no latency impact. So when we do dynamic or global load balancing, it's all happening at the granularity of the data plane. So it's the data plane that is making that decision. So there is no impact to latency of either DLB or GLB.
Okay, great. Did have another question. I think this is maybe a bit more for Samay. When you mentioned non-NVIDIA vendors, can you elaborate a little bit on who you might be talking about?
Thanks for the question. So that allows me to clarify what I meant by that. I was referring to the accelerator side. And what I meant is that we're seeing more of the, let's say, AMD and even the hyperscalers building their own accelerators. That's what I meant by non-NVIDIA GPU or non-NVIDIA accelerators. And once you are building or you are running non-NVIDIA accelerators, most likely you will be also using Ethernet. Not in all the cases, but we're seeing a higher attach rate of Ethernet on the non-NVIDIA accelerators than what we're seeing on the NVIDIA accelerators, obviously. So that's what I meant by that.
Okay, thank you, Samay. This is a bit of a side question, but I'm not sure, Praful, if you want to talk about this a little bit. People are asking about liquid cooling and networking, and I'm not sure if Juniper has taken a look at, what would happen if we need to put Ethernet switches in immersion tanks or use cold plate. Is there any activity around that you care to comment on?
Yeah, I think liquid cooling is one of those things that is, coming, and it never comes. But I think now it will finally come. I think immersion is something that only Juniper has tried, but it is more in, I think it's more in a prototype and experimental stage. But liquid cooling is going to happen in the next generation, is what we are seeing. So we are bullish on liquid cooling, and I don't want to give away too much of our Juniper roadmap here, but yes, I think liquid cooling in the next generation, once we get to 1.6 terabits, is going to be relevant. There's a cold plate liquid cooling, by the way. Yeah.
Okay, and one more thing that maybe we could chat a little bit about is the use cases and timeline that you can share, Praful, or Samay, from your discussions with your clients that are rolling out. Are there particular use cases that are getting more traction, maybe in medical or other areas that are worth mentioning that you've heard about?
I can start. I mean, From some of the general overview from some of the discussions I've been having, if you're looking at applications in enterprises, some of the vertical industries that are really investing heavily, at least in the short term, on AI. As I mentioned, that we are seeing governments, we're seeing finance, we're seeing healthcare, we're seeing automotive, right? Those are some of the broad vertical industry categories where we're seeing really fast initial AI adoption and applications. I'm sure other vertical industries will follow suit, but at least from what we're seeing most recently, those are the major verticals.
Sorry,
Raful, if you want to add.
nothing more to add. I think I do agree with you. It's those verticals.
Okay, well, I actually have a use case that I can share that I've come across in the medical industry. It's about helping and integrating AI into the life of the doctors and the healthcare practitioners. And what I was told by some of the medical professionals that I've been talking to is that, when they see a patient, they have to invest a significant part of the time after the patient leaves documenting that visit. And what they've started to do is have an AI agent listening to the actual interview, the medical interview, doing the transcription. And because medical records often follow a very particular structure, the AI is really able to fill in actually most of the report of what happened with the client. And if during the interview, the doctor would say, well, I want to prescribe this much medication for you of this type, actually the AI system will actually fill out the lab request report. And so when the patient leaves, the paperwork is pretty much all mostly done, and the doctor has to just verify that everything is correct. The other flip side of that is what I was told by a number of medical professionals is, let's say they have a complicated patient coming in for a consult and they haven't seen the patient for a little while and there's been a lot of tests written. They could spend up to 30 minutes going through all and finding the reports and understanding where the patient's at before they meet them, whereas they've been using AI to summarize everything that's happened before they reach the patient, so that in 5 or 10 minutes they can get a summary very quickly, and that saves them an enormous amount of time. So that's two use cases that I think give us a very real feeling that in some cases AI absolutely can integrate into our daily lives or professional lives and accelerate or improve how we do things. So I thought I could share that. With that, we're just about near the top of the hour, and I would like to thank Sameh and Praful for the discussion today. For everyone else, thank you for attending. We will be having this posted later at the website. It'll be available on demand, and we will continue to promote it. So thank you all for attending today.
Thank you.
Thank you.